I'm going to talk about this fluid structure coupling and control aspects of this coupled system. I think that this is an appropriate topic for ICER especially, because various applications in Trivandrum, space research and so on involve such coupled structures. Okay, so first of all, I would like to thank the organizers for providing me this opportunity to speak at this event. So here I am going to present the work which I have been doing with my French collaborators. Hervé Dosa, he is in CNRS Toulouse. Remo, you know him very well. And Tuxnak. Okay, so earlier I gave the title on Helmont's model in fluid structure coupling. Finally, I changed it and I decided to speak on something more general. But then, of course, the essential model I will go into is Helmont's model. Okay, so what is this fluid structure coupling? So what I plan to do is to start with something more complicated, and finally, if you want to do finer mathematical analysis, you have to go down to a simpler model like Helmont's equation, Helmont's model. Okay, so I start with this one of the celebrated models of fluid structure coupling, namely Navier-Stokes equation for incompressible flows coupled with the Lamé system of elasticity. So I just write down the equations. So we have, so you have to imagine a picture like this. So you have a container of fluid. So there you have a solid body which is flexible, okay, elastic, flexible. So what it does is that it executes a motion like that, right, inside the fluid, and we want to describe that. So as it moves inside the fluid, it deforms and so on. So we want to study this. So what is the corresponding model? So you have a fluid region. So this is the fluid region. And this is the solid region. So, so we are inside R3, and this is the solid region. Omega is the union of these two regions. And I have written down this incompressible Navier-Stokes system here in the fluid region, omega F. Okay, so here is the usual stress tensor for the fluid, which is given by the Newton's law of viscosity. So that is the description of the dynamics of the fluid. Now, let's go to this dynamics of the solid straight away. So you have what is known as a Lamé system. So this is the usual wave equation. Only thing is it is system now. So W denotes the displacement of the system. And there is a solid stress here, Cauchy stress, which is expressed in terms of strain according to this linear relation, and you have the strain here. So this is the description of the dynamics of the solid, and it is in omega S0. The difference here is that this is equation, the V is the velocity, is described in the Eulerian domain, and here it is Lagrangian variable. Okay, now we have to couple these two. So in order to do the coupling, namely that as the solid moves inside the fluid, you must have continuity of the speed across the interface and continuity of the stress tensors. So, both solid and the fluid. So, that is what we have to formulate. Okay. So, for that, it's not easy because the solid is moving. The interface is changing with the time. So, we introduce this Lagrangian trajectories associated with this vector field of the fluid, okay, and this connects the variable x, Eulerian variable, with the Lagrangian variable y, and the y comes as the initial condition here. Okay, so given that, okay, let us look at the boundary condition. So the fluid sticks to the outer boundary. Outer boundary is this. And here is the equation which says that the two velocities are same. So I told you W is displacement of the solid. So I look at it's a derivative with respect to time, and then put it. And then here it is V is a function of x. So I have to move. This is defined only with respect to y. So I have to move the point from y to x to demand this equality. And similarly, I have to do the same thing over the for the stress tensor. I have to move, and when you move that, because of the normal derivative, this is how the normals transfer, right? I mean, cofactor of this Jacobian matrix. Okay, so this is the it's a pretty complicated nonlinear coupled system. It's quite difficult. Okay, quite difficult. So what I am going to describe is some of the obstacles which we have come across, and it is a work in progress. There are some slight technical points, and we are sure that that can be overcome. Okay, so I want to just to briefly give you some ideas about this system. So here are the some of the features. Okay, so first of all, it's evolution problem. There is a time, and the interface varies with the time. So it is really a time-dependent problem, and it's not in the standard form. Okay, the domain is varying, so it is not omega cross 0t. No? So it's a non-cylindrical domain in space-time. Okay, so that is one aspect. Another aspect is well, free interface. Interface is a part of the unknown. So you cannot have a fixed state space, subular space, and then work with that. That's not possible. And then this is due to coupling. Okay, we have parabolic problem, which is the dynamics of the fluid, and then hyperbolic problem, which is the dynamics of the solid. So you have a mixed nature, and well, I mean, if you look at the corresponding space-time, you have two different metrics. You have to patch them up at the interface. And if you want to look at asymptotic solutions, you have to worry about the corresponding scalings, and they are different, you know. And then characteristic speeds do not match interface. And some of the natural spaces which born out of these energy considerations, they do not match at the interface. So there are plenty of problems with this kind of coupling. So I have just these are all general difficulties in any coupled system. Okay. So what is the general method of attack for this kind of problem? Okay. So there are a lot of papers on such a coupled system, not necessarily Navier-Stokes coupled with Lame, but generally coupled system. But there are always some restrictive hypotheses. General problem is open. General problem is open. But then I tell you what we have solved. Okay. So first of all, if you want to solve such systems, okay, here are some of the ideas, some of the hypotheses under which you work. So you have to assume something is small. Okay, solid deformations may have only finitely many degrees of freedom. So that means that you have the infinite system, infinite degree of freedom here on the fluid, and you have finitely many degrees of. So it is a question of coupling parabolic problem with a finite dimensional system instead of full hyperbolic system. So that is manageable. Okay. So in that sense, hyperbolicity is negligible, parabolicity dominates, and solid is treated as a perturbation. So what we have done is that we have validated we do not a priori have any such restriction, but we have proved well-posedness of this coupled system for a small time, okay, small time. So in other words, we do not allow these solid deformations to grow arbitrarily. So if you allow to grow, then the problem is open. We don't know. Problem is wide open. As far as my knowledge goes, there is no paper dealing with such. Okay. So what do we do here? Okay. So let me just give you some idea of our procedure. So we take this coupled nonlinear system. So there is a Stokes operator on the left hand side. So we look at the corresponding linear operator. So we have a Navier-Stokes. So we take out the Stokes, and then Lamé system is linear, fortunately. Okay. And then we put all the nonlinearities on the right hand side. And then we show that these nonlinearities are Lifschitz with a Lifschitz constant which goes to 0 as t goes to 0. So that for t small, we have a contraction, right? Lifschitz constant is small. So we have a contraction. And so we apply a fixed point theorem. So the crucial thing here is that you should judiciously choose the right functional spaces. And because of the difficulties I told, this is the essential part of the work. Okay, if you hit the right function spaces, you should be able to define all these. You should be able to prove all these properties. So that is the main thing here. So with this idea, we proceeded, and then we are not able to prove this kind of geometrical configuration. We are not able to handle. On the other hand, what we can handle is the following. So what we call a sandwiched fluid solid structure. I am just drawing the figure in 2D, but then you can add one extra dimension behind. So you have a solid structure which is right in the middle, and then so we suppose along the horizontal coordinates periodicity boundary condition. So there is a torus here, and then with respect to this we have physical boundary conditions. So this is the problem which we could solve for various reasons, and mainly the coupling. So I told you we have a Stokes operator for the fluid. So given a fluid state, we come back to the solid state. So let me show you the. So given the fluid state here, it defines a Dirichlet boundary condition for the, if you integrate with respect to time, Dirichlet boundary condition for the solid. And then go back to the fluid, sorry. Where is it? Yeah, here. So, so this is known coming from here. So you take a Dirichlet boundary condition for the solid, you solve this, you get the Neumann condition, and then put it back into the fluid. So this is the idea. This is the iteration process. And so you see there is a study to be done for the Lamé system, Dirichlet to Neumann map. This is the problem. And this is something which is well known among control community.
So the diaphragm is allowed to deform.
Of course, that's the main thing. Yeah. I am just drawing in y variable, which is the initial configuration. So it goes a little bit up and down. Okay. So, and the fact that it cannot deform too much, it's all because of this map, Dirichlet to Neumann map, which we are not able to study. So, because of this one restriction, we have to deal with such configurations. Okay. So, it's in our opinion, it's a technical problem. But then I just want to tell you that there is a live, open problem here. So, let me go into, the situation is not that hopeless. Let me go into some simpler baby models. So, we can, instead of saying that I restrict my time, small time, or restrict the solid deformation, I make the solid deformation 0. I look at the rigid bodies, no solid deformation at all. So, in that case, one hopes to prove global results, right? Global results. Okay, so here is the model, the same model which reduces to the following one. So, so you imagine the first configuration. Now the solid is no more elastic. So there is the boundary which is rigid, but it moves. Okay, so xb is the position of the center of mass, and the omega is the angular velocity because a rigid body. So these are the three unknowns, right? Q is the orientation of the solid. So solid can move, solid can rotate, and so on. So here is the position of the solid expressed in terms of its position at time t equal to 0. So via Q, it gets rotated, and via xb, it gets translated. And this is the change of variable. This is the Eulerian current configuration, and y is the variable in the initial configuration. Okay, and we have to find the equations for these things. Okay, so sorry, here it must be mass times xb double prime t. So this is the Newton's law, and because the thing is solid, so this is the way Newton's equation. So the fluid stress contributes to the boundary like that. The only force acting on the solid is through the boundary, and it is this. So here you take care of this interface boundary condition which I described in the earlier model. And similarly, you have evolution equation for the omega, angular velocity. So you have to look at the corresponding torque here. Torque here. Okay. So here are the equations, and for Q you have this equation. Q is the finite rotation, and omega t is the angular velocity, which is the infinitesimal rotation, and this is the equation, linear equation given omega for Q. Okay. So you have a beautiful set of equation, and the philosophy is that according to the general philosophy, this should be solvable globally. Yes, indeed. And this is the work of this Tuxnak and his collaborators. I am not saying that they are the only ones. What I am saying is that I know, I have collaborated with them, so I know them. So they have done a lot of things on this area. Okay, let us go further. So Stokes model. So here you have to imagine something like this. Okay, so you have a tube. Imagine a tube which is put inside a box. Okay. So you have a 3D box, and in the middle you have a cylindrical tube, and now the tube is fixed at both the ends, and there is a fluid flowing across the cylinder. And we assume that the cylinder is of large height, so that I can that the boundary effects from the top and bottom are not felt in the middle. So I look at the two-dimensional cross section. So problem is simply, so this kind of model I owe to my French collaborator, Blanchard, who is no more. Okay. So here is the Stokes model. So you see a Stokes equation. Okay, here is the control. You can put the F or some 0 here. It doesn't matter. And this is the incompressibility condition. And this is the y equal to s. So the velocities, two velocities coincide at the interface. That gamma I is the interface between the solid and the boundary and the fluid. So this is the initial condition. This is the boundary condition at the exterior boundary for the fluid, and you have initial condition. And then for the solid, this is the so Blanchard was an engineer in electricity company. So there he ran into this kind of problem in nuclear reactors or heat exchangers and so on and so forth. So the practical problem is that you have to increase the interface between the solid and the fluid. If you want to transmit a lot of heat from the solid into the fluid, right? And then you have to evacuate the fluid. So in a small compact box, they have plenty of tubes. That's the idea, plenty of tubes. And they interact. Okay. So this was the practical problem. And of course, this is when you have a large number of tubes, automatically the problem calls for what is known as homogenization, which we have done separately. Okay. Now here is a control problem. So the tube it's fixed on both ends, but it is vulnerable to vibrations due to the fluid motion. So it vibrates. So that is modeled by this. And so that is the solid dynamics, and this is fluid dynamics. And here is one coupling. Here is the another coupling, which we have seen already. Okay. So that is the Stokes model. Now, what we have done with Remo is that straight away we were not able to handle this. It was somewhat a difficult problem. So we first started with this baby model, which is a baby version of that Stokes model, in the sense that there is no pressure effect. There is no divergence-free condition. There is no pressure term. Otherwise, it is the same. Only thing is we have to artificially cook up this contribution here. We have to find a suitable replacement because we are eliminating pressure. So what we have done, we have looked at the heat equation with this coupling condition, and we have put this artificial term here. Okay, so this imitates many features of the earlier model, Stokes model, but simpler to deal with mathematically. So we studied a control problem for this. Okay. Then comes this Helmont's model, which is very nice, idealistic, but very nice to have insight, first insight into this coupling business. So what does it say? So I have a Helmont's operator or D'Alembert-Schian here for the fluid. So that means I am looking at this sound propagation in the slightly compressible fluid, and I have a control term here. Let's not worry about it. And so y is the fluid potential, velocity potential. So this is somewhat arbitrary, artificial, but we will assume that for mathematical nicety. And then since the fluid is inviscid, you cannot say that the full velocity fields coincide on the interface. You can only talk about the normal component. That's what we have done here. And then initial condition for the fluid. And this is the condition, which is something like this, which we borrow here. Okay. In the inviscid case, when you linearize Euler equation, you can drop the nonlinear terms, and what you have is only pressure remains, right? only pressure remains because nu equal to 0. So, this only pressure will contribute here, and the pressure can be equated to this minus y prime through Euler equation. Okay. So, this is the kind of model which is which has performed quite well, reasonably well. That's what my collaborator said. Okay. So, I just resume the various properties of these things. So, from Navier-Stokes coupled with Lame, that kind of coupled system, you first go to this. So, you make the deformation, there is no deformation, and the number of degrees of freedom for solid, for elastic solid is infinite, but here it is only finite. And then we, from this model, we go to Stokes. So, here we have some degrees of freedom through vibration, I told you, but of course, it contains viscous effects. And then from Stokes to heat solid model, we eliminate pressure, no incompressibility condition, but we keep viscosity effects, and through this vibration, some solid deformation is allowed. And then from this model to Helmont's model, okay, we add a small compressibility effect, and then through vibration, some solid deformation is allowed. But importantly, we eliminated viscous effects. So, here there is the general ideas of dealing with the various terms in the coupled model. So, if you have a nonlinear equation, if you have a nonlinear equation, of course, you will linearize and study local controllability, local properties of the equation for the nonlinear system, and you pray that the linearization principle holds. Okay, the most very important things are happening when linearization principle does not hold. Oh, that's the recent advance into these areas. Okay, if you have viscous effects, you have to worry about this monster Karlman estimates. So, we are not going to into all those things, but in our paper, we have done all these things. Okay, so with all these things, let me come to this Helmont's model, where there is no viscous effect. This Laplacian is not viscous, it's part of wave equation, and there is no pressure. There is no pressure. So, the fluid vibrates through this, and the solid vibrates like a harmonic oscillator, and there is a coupling between these two. So, this is the roughly the physical model, physics of this system. Okay. So, from now on, the usual mathematical thing. Okay, so we look for energy, right? Energy conservation. In all mechanical models, that's the usual trend. We go into some a priori estimates. That's what we. So, you do the same thing here, and the quantities which appear dictates this space. So, this is for the fluid, of course, this fluid potential. We are looking at the velocity potential. So, that is the space, and this is for the impulse, okay, the time derivative of the potential. And I told you, we are looking at the cross section of that fluid structure. And so, we are dealing with a solid displacement and the velocity. They are two-dimensional vectors. So, in the model, it is this S. S is in R2 vector, two-dimensional vector, and you have a coupled system here. Okay. So, you have energy conservation. In fact, it is the matrix which operator which defines this is in fact a skew adjoint operator. And so, everything is known by a simple application of classical Stone's theorem, which says that any such, if your infinitesimal operator is a skewered joint, then the dynamics is well defined, and in fact evolution is unitary. Okay. Now, for exact observability for such systems, yeah, the usual thing is that you approach through the observability of the system, and so we are worried about this aspect, observability. Now, I have here three types of results. So, the third result, of course, is the improvement over the other two. Okay, so that is what I am going to. So, what are the results, and what are the ideas to reach these results? Okay, so observability is the aspect. So, you consider the free dynamics. That means without any control. So here, so I put 0 here. So this is the system rewritten, Helmont system rewritten with the initial conditions. So here is the observation estimate. Observation estimate. So first of all, yeah. So you look at this phi prime impulse and its energy over a period of time in a space region U, and you want to dominate the energy in terms of this observed quantity. Okay, so this is interpreted as an infinite dimensional Kalman condition. Okay, so what is it in the observability estimate? Okay, first of all, observability estimate should imply unique continuation principle, right? I mean, in fact, if it is 0, then these initial conditions are 0. So, if the initial conditions are 0, because we are looking at free dynamics, there is no other inhomogeneous term here, so everything must be 0. So, that is the so-called unique continuation principle for this system. Okay, and proving such a principle itself is not easy, as anyone in control theory can vouch for that. Okay, so the main thing is that why such an estimate should hold. So obviously its validity depends on U and T, the region where you put the control and the time of controllability. So these are the things unknown, we have to worry about it. So in the first installment of the work which I have done with Remo, we have looked at this case. We have put the control over the entire domain, and in that case, even though the system is hyperbolic, harmonic oscillator coupled with the D'Alembertian, so there is a finite speed of propagation, but the control is acting everywhere. So as pointed out by Maithili yesterday, you expect exact controllability for any time t positive arbitrarily small. Okay. So that's it. So you have so this is a general theorem. Here I just recall that observability. If you have observability, you have controllability. So suppose observability estimate holds with this U and T, then you have L2 control. I recall that control is here. This is the right hand side, interior control. Of course, one can do boundary control and so on and so forth. I am not going to mention it here. Okay, so there is a control in L2 with the finite energy, such that you can bring the system to the rest. In fact, how U is obtained, so this is the philosophy behind what is known as Hilbert uniqueness method of Jacques-Louis Lyons. So it is the following. So you want to estimate this initial condition, so you define the strategy is optimal control. You have to devise a suitable optimal control problem for a particular J, which is this. cost functional, which is this. So we are looking at free dynamics. So this is the impulse coming from there, okay, and phi naught, phi1, and then y0, y1, s0, s. So these are the corresponding variable in the Helmont system, okay. Now, if you catch hold of the unique minimizer for J, which is denoted like that, and let phi tilde, W tilde is the corresponding solution to the Helmont system with this initial condition, then you take U equal to your control, this phi tilde restricted to your domain. Now, where is this observability estimates coming in? So one knows that exact observability estimates is the one which implies the coercivity of the functional of this functional. So your minimizing sequence for the functional, it guarantees a stability of such a sequence. So that it plays a very crucial role. Okay, all these things are well known, and now the question is how to prove this observability estimate. So this is the one which guarantees the coercivity of the function. Okay, so proving observability estimate. So the first method which we have followed is the usual multiplier method. So you look at the free dynamics, phi and free dynamics for phi and s. You multiply by this rho phi rho s. You integrate by parts. Well, there is a whole machinery which one has to go through. At the end of it, you get this inequality. We are not done yet. Remember that we wanted this. So in other words, we have to get rid of this extra term. But that extra term is finite dimension. Finite dimension. It's solid which is inside the fluid, finite dimensional. In fact, it is R2. So it is governed by some ODE. So we can use the usual thing, the compactness argument, which in fact can take care of any compact term, compactly embedded term. So in particular, finite dimensional term, and using that, you can eliminate this, and that energy is dominated by the fluid energy. So this is what I said, that every time you tend to prove this kind of inequality. You tend to dominate the solid by fluid. Unfortunately, all the mathematical techniques are like that. Otherwise, we are not able to make any progress in the field. Okay, so this method works for this multiplier method. This works and then establishes the observability estimates if the control domain is the entire fluid domain. And of course, this is the advantage. T is positive. But then this is not practical. Okay, so the next step was to reduce the control region. Control region. Okay. So here comes the second method. So first method, control was, so I look at the cross section. So control was everywhere, entire fluid region. Now, the second method, we have a control region like this. A neighborhood of the boundary of the solid and a neighborhood of the boundary of the fluid. Boundary of the fluid. So we have to, how do we reduce to this? So that is what I'm going to explain. So, frequency variable method. So with respect to time, the system is homogeneous. So we can use Fourier techniques with respect to time. That's the idea. But then, as one might expect, you may reduce this control region, but then you will lose all information on the time of controllability. This is the defect of the method, right? I mean, we are looking into the, it's a dual variable. Okay. You have to pay the price. So you look at the Helmont system. Now we go from T to omega. Okay, so here is the theorem. So U is a neighborhood of the boundary of the solid and the boundary of the fluid. So control region is definitely reduced. And then there is a time of controllability. It is not for every T positive. Now there is a time of controllability. Of course, this is expected because we are dealing with a hyperbolic system, such that we have observability, hence a controllability. On the other hand, you have you cannot estimate this time. That's the problem. Okay, so how do we proceed? So you write Helmont's condition, Helmont's model as a first order system. Here with fluid variable here and then solid variable there, and then this infinitesimal generator like this with its domain in all its glory. And then what is this the term which contains the control and the corresponding operator over there? B is the following. So it's a kind of restriction of V over the control domain, and its adjoint is like this. You have again, I already remarked, the free system is defines unitary evolution. Okay, now to prove the required estimate, we go from T to omega, and this is known as Ortiz test in control community. And I collaborated in this part of the work with Tuxnak, and they have written, he has written a beautiful book with Weiss on such topics. Okay, so what is the idea behind the method there? So essentially the complication comes because we are dealing with the infinite dimensional system. So what we have to do is to look at, the essential idea is to look at the high frequency part of the solution and separate it from low frequency part. So this is possible because we are dealing with frequency variable. So here is some conditions are coming up. And so in other words, observability estimate is split into two other conditions, one corresponding to high frequency part, another one corresponding to low frequency part. So this is the idea. Now, so generally you have a system like this with this skew adjoint operator over here and the compact resolvent, and you have a basis of eigenvectors and the this one and the corresponding eigenvalues. Then you, for each lambda, I can define this space. So this contains a high energy modes phi k, because the corresponding frequency spectrum is larger than lambda, and you have the corresponding inequality. So this reminds of this observability estimate. I am estimating phi in terms of various other quantities, but we don't have time. Instead of time, we have frequency omega. So it says that there exists a delta and alpha. Delta is this constant. Alpha is a constant which defines the nature of high frequency, and we demand this estimate. And then corresponding low frequency condition, it simply is that it couples the operator A with rather B star. This is the free dynamics operator, and this is the control operator. So observability operator, because B star. So we have B star phi is not equal to 0 for every eigenvector phi of A. So that is the. So if these two conditions are satisfied, then we have exact controllability and exact observability. Whatever observability I wrote down, it's valid. So in other words, the novelty here is these two conditions. Okay, so how do we prove this? So let me take this low frequency condition. So I have to take any eigenvector of phi, and A is skew adjoint, so I take eigenvector, and then okay, I rewrite the system like this because A is a scalar now. A is a scalar. As far as this phi is concerned, it's a scalar. So the system reduces to some algebraic things like that, and one can prove that 0 is not an eigenvalue for our operator A. And so if B star phi equal to 0, that's why I calculated B star earlier here. So use that, which says that something is equal to 0 on U, and then there is this in the frequency, your wave operator is something like this, Helmont's equation, with f equal to 0 on an open set. So the classical unique continuation principle ensures that f is identically 0. Once f is identically equal to 0, you go back and check that the entire, all the other components is also 0. Okay. So the condition number 1 is more delicate. Okay, that's technical. That means the high frequency condition. High frequency part of observability is very delicate. And so you have to prove some inequality. The mathematicians' delight would be to argue with the contradiction. And it is, of course, technical. And what roughly I tell you, in high frequency part, the coupling can be neglected actually. Helmont's model is an uncoupled model. So you have D'Alembert equal to 0, y equal to 0 on the exterior boundary, and the corresponding uncoupled model is this, Neumann condition equal to 0 on the interface. Okay, it's not, I cannot easily convince you, but you have to take it for granted, this. And then the choice of U, the two boundaries are covered, neighborhood of the two boundaries is appearing here. And these two put together implies your observability estimate for the high frequency mode. Okay, the last tip. So this part, in the nuclear reactor model, you cannot reach this. It's inside, inside that domain. On the other hand, this part is accessibility. So the question is, can you eliminate this control domain? In other words, I want to establish the observability estimates only from here, with the control here, observation here, not here. So that would be, that question is motivated from practical considerations. Okay, so, this is one of the things I learned from Planchard. So what do we do here? So in other words, as the system vibrates, in a complicated thing, some energy can be trapped in the neighborhood of the solid. And that's a danger signal. You cannot control because you are applying the control only at the extreme. So we have to show that such things do not happen. In a general configuration, we don't know. We don't know. So that is why this important hypothesis H of some symmetry. If your disk, your solid is a disk, then everything goes well. No trapping of energy in the neighborhood of the solid. So, and in order to prove that, we follow this method. So this is the so-called, it's a big name for a simple idea, which I will explain later. So the theorem now is that the latest theorem for Helmont's model and its control aspect is this. Let U be a neighborhood of the external boundary only, okay, outside boundary. No control near the solid boundary. Assume that this solid is a disk. Then observability estimate holds with the optimal time. Optimal time, it's well known from geometrical optics ray propagation. So, so that is well known. So with that kind of natural time, you have this is the result, ideal result one would expect. But unfortunately, we have this condition. We don't know how to eliminate that. If you do not have any such thing, then the problem is over. Okay, so here is the interpretation. So this hypothesis ensures that no energy is trapped near the solid boundary. You must remember that it is not the usual boundary condition, geometrical optics propagation. It's not that. There is a coupling in the, so that's the entire exercise we are doing. So it's not clear that if you remove this thing, whether the energy is trapped or not, we don't know. You have to study always through the coupling. Okay, so So here I say that we need a control only on the neighborhood of the external boundary. Okay, so what is our idea? Because we have imposed H, which is a symmetric assumption. So naturally, it is natural to use polar coordinates. We are in R2, and so it's called for polar coordinates. And we decompose the system in terms of spherical harmonics. Surprise. So this is inbuilt in Helmont's model. So what is a surprise? So only the first harmonic mode of the fluid is coupled to the solid. Okay, all other modes are free. So you know the free equation how to solve, because the literature on free dynamics is enormous. So we know how to handle the free modes. It's a technical, but one can do that. On the other hand, for the coupled mode, one single mode, so we have to, let us say, one space variable. That's the whole thing. There is only one space variable which is coupled with the solid, but then we are working in the r theta coordinates. So this is the equation, and this is the coupling. This is the coupling, but it's one space dimension, r. So this is the let us say, the important reduction in the Helmont's model with that symmetry assumption. If you do not have the symmetry, of course, none of these ideas will work. That's the problem. Okay. Now, I told you that if you have, so the method is this method of lateral propagation of energy, which means that if you have a wave type equation in one space dimension, the time is also one dimension, you can interchange them. That's the whole idea, right? You can interchange them. So you have the standard quantities like energy and so on and so forth, which are defined for t constant. For each time slice, it is defined. Now you interchange the role, you fix r and then define it in terms of t. So you play the game. I mean, this is several people have played, and we also have played with this system. And you get this observability estimate for this one-dimensional system. And in particular, okay, it looks complicated, I cannot go into. So in particular, for the optimal time, you have observability, unique continuation principle, everything. Okay, so this is the estimate. So that's what so lateral propagation of waves, interchange of space and time, and then integrate energy density with respect to time at a fixed space point. So this is what is known as a lateral propagation of waves. So we have, I finish with the conjecture. So we feel that if the solid is not a disk but any convex region, we still feel that there is observability estimate with the optimal time. Okay. Thank you for your attention.
Questions? You can conduct. Questions?
You put up the spherical solid for a small
Yeah. We hope so, yeah. I don't know. See, the thing is that I told you this surprise, it works only with this, for this. So if you perturb, you don't have a surprise. This, of course, from this you can perhaps do some perturbation analysis. Yeah, we are thinking along those lines, yeah.
What's the status on the solvability? Is just rigid
Which
body?
one? Which one?
Rigid bodies or less bodies moving inside fluid.
See, there are papers, but the subject is technical. I told you it's highly technical, and that's why it's taking so much time. So, for instance, there is a huge paper by this. In archives, 80 pages. Yeah.
You see Davis, yeah.
Huge paper with all sorts of estimates, 80 pages. And they also prove local solvability for Lamy and Navier-Stokes. But we are not satisfied with their proof because I don't know. I mean, it seems to contain some uncorrectable mistakes. So it's open. It's open. The configuration, the sandwich configuration, because they deal with this. In our opinion, it's open. We could do only this because of that Poincare, that Dirichlet to Neumann map, which captures the real essence of the coupling. One has to analyze that. One has to analyze deeply. It requires a lot of insight into this physics of the problem. No?
So you said that geometry is motivated by nuclear reactor.
Yeah. I mean, this is the standard one. The solid wandering through, I told, this kind of motion is the standard one which people expect. But if it reaches the boundary, of course, the model breaks down. It's no more continuum mechanics. But then before reaching the boundary, people expect to prove such a result. In fact, I was inspired by this notebook given in this conference. There is a fluid and a solid is falling and then drops are coming out. I wonder, I am dreaming about a day when such results can be proved mathematically.
They could break up and so on.
Yes, exactly. Yes, it's an open problem. Yes.
Any other question? If not, let's thank the speaker again. Tea time. Training for tea.
Thank you. Good job.